presentation on the camera. Put this on. Heavy duty cord. Okay. But when I got here, as soon as I bring this thing in the classroom, it's working.
Wow.
So. Hello, Jocelyn. Talk to me, Jocelyn. I need to know if it's working.
Hello.
Okay, let me see.
Is anybody else in there?
There's one person in the classroom and one person on Zoom.
Nice.
Now, was there somebody else out in the hall that was here?
I think there was, but I don't know if that person was.
Yeah, sir, I'm gonna be honest. I'm kind of broke right now, and I've been coming home to take the class because that's where the food is.
Huh? Yeah, I hear you. Oops, wrong button. Wrong button. Hi. I have a camera pointed right at you. It's just like. That's good. Oh. Five classes I teach, 3 of the PowerPoints. Remember where I left. This is not one of those. Difference formulas. And we did we do some of the difference formulas?
I have to see.
Sine of alpha plus beta, sine of alpha minus beta, cosine of alpha plus beta, and cosine of alpha minus beta. Yeah. And tangent, we covered tangent as well.
What's going on, guys? What's up, sir?
Sun and the moon and the stars.
Sun and the moon, stars.
Let me pull this one. Oh, it helps if I turn the damn thing on. Then I don't want you down.
One second.
Move it up there slowly.
Not necessarily sure. Once they stop. How come, sure?
I saw that movie in the theaters when it first came out.
Really?
So funny.
You were having in movie theaters?
That was a long time. It was a huge,
If you what?
it was a huge deal. Airplane,
Yeah.
when it first came out, it was huge.
Everything.
What?
Everything. Like
Well, because that kind of humor you never saw in movies.
and you'll never see it again, sir.
Oh, yeah, you do.
Sir, not how like kind of.
Well, not
racist
the
they
same
are.
way, but
Like that, yeah, that.
that. Surely you don't mean that. Yes, and don't call me Shirley. You know, that kind of, that absurdist humor. Mel Brooks was a master of it.
Was he the director or the writer?
I don't know if he had anything to do with it. But he had a short-lived TV series called When Things Were Rotten. And it was done, and it was loosely, it was Robin Hood story, but with absurdist humor. And someone said, what are y'all are doing? Oh, we're hanging up the banners and hanging the banners on the wall. And you walk into the room and there's this man and wife and three children. Say, hi, I'm John Banner. And
Oh my
they hung
God. Yeah.
yeah, so it was hysterical. But anyway, History of the World Part 1, and there was never a Part 2.
Really?
That's a Mel Brooks movie. I don't think he ever had any intention to make Part 2. Silent movie?
Sir, I don't know about that one. I'm sorry. I just know the airplane one. The
Well,
airplane two.
no, it was a long time ago. It was before those movies even. It was literally a silent movie, but the only words spoken in the movie, you know who Marcel Marceau is?
Sir, I'm not-
No? Okay.
No idea.
Well, he was a world famous mime. He's the only person in the movie who said a word. And it was no.
Oh,
It was just a single word. But the whole movie was, and so there was, you know, you had the placards that would show up that would have the conversations on them and that sort of thing, like old time silent movies did. This is before they did the closed caption across the bottom subtitles.
Yeah.
But yeah.
awesome, guys. Oh, Mr. Good kicking ice cream.
It was full of sight gags.
Psych gags?
Sight gags.
What's that, sir?
Oh, like pratfalls, that kind of stuff.
Pratfalls?
Oh, man,
Sir,
you are
I'm
uneducated.
uneducated. That's why I'm here.
No, slapstick,
Okay, okay. Getting closer.
humor-based, physical humor,
Okay.
where somebody gets hurt.
Oh, classic. Love it.
Slapstick. Someone falls down and this.
Yeah, so like, yeah, when someone falls down the stairs or someone trips another person, they're like, ha 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 ha.
Chevy Chase is good at slapstick humor,
Okay.
where he falls and stuff like that. When he hosted Saturday Night Live, well, when he was on Saturday Night Live, he would do President Ford, and he would always fall down. So that's pratfall.
Sorry, I know who Chevy Chase is. Okay, don't. I'm good. Bye.
See, I was in college when Saturday Night Live first aired. And when Eddie Murphy was on there, that was about the time we quit watching. My wife and I, it got mean. It wasn't so much funny as it was just mean. And I think they've come back. We watched a couple of episodes recently. When they have a host on or a musical guest, that was fun to see.
Yeah, some of these.
But okay. I'm just remembering some of the commercials that they would put on.
Put on when?
Fake commercials that Saturday Night Live does. Okay, if you're on Zoom, please be sure and put your name in chat, as well as pin my screen. And the camera is working today.
Yes, great.
Yes, mainly because I honestly feel it came on because I brought this is a presentation camera, it's one that hooks up to it.
Yeah,
Does basically what that does.
sorry, I like that one. It looks like it belongs on something that goes to NASA.
Yeah, it's got that armature stuff. Okay. Did we cover this?
I don't remember so much.
Yes, sir. Yes, sir.
I don't believe so, sir.
Sine and tangent, cotangent. Oh, no, it's not cotangent. We have two formulas for the tangent of the sum of two angles and the tangent of the difference of two angles is those two formulas. They're the same except for where the plus and minus are. Okay, so you have plus and minus in both, but if you're adding the two angles, the plus sign is in the numerator and the minus sign is in the denominator. So you're adding the tangent of the two angles and you're dividing that by doing 1 minus the product of the two tangents of the
Have
two
we heard anything
angles.
from Robert? Sorry, did you stop?
No,
Nothing?
I haven't seen it.
All right.
I don't
Just
remember.
checking. I'll wait
Yeah.
about 20 minutes.
Okay. Okay. And so, and if you're taking the tangent of the difference of two angles, then it's the difference of the tangent of the two angles divided by 1 plus the product of the tangents of the two angles. So. Okay. I am
Sir, we can't hear you. You're muted.
How'd I mute myself? I didn't touch it at all. Okay. But I forgot what I was saying, but it doesn't matter. Okay, so using the tangent of a sum formula, the numerator, I can find the term that writes.
Oh, sir, I knew today felt weird. When I woke up this morning, it was weird. And the weather, just weird. Everything's weird today.
I got to school by 7:30, which was really weird. That never happens.
Hey,
I have an 8 o'clock class. And then I have this class.
oh,
Tangent of theta plus pi becomes the tangent of theta plus the tangent of pi over 2, right? Because it's, pi, sorry. Tangent of pi divided by 1 minus tangent theta times tangent pi. Well, what's the tangent of pi? It's not right. Well, the tangent of theta is just going to be the tangent of theta. But what's tangent of pi? Pi is over here. What are the coordinates of this point on the unit circle?
-1,
-1,
-0.
0. And tangent is, in terms of x and y, what is tangent?
Y over X.
Y over x. What's the y value here? 0. So this is 0 over -1, which is 0. So I'm just adding 0 here. So that just leaves me tangent. Here I'm multiplying a tangent of theta. Tangent of theta, we're going to multiply by 0. So this goes away. So all that's left down here is this 1. There, we did it. So they actually wrote it out, which I probably should have too. Tangent of pi is 0. And so you have tangent plus 0 and tangent times 0. So you just get tangent theta over 1, which is tangent theta. Okay. Now, what do we want to show this equals? Cotangent.
Negative cotangent.
Oh, negative. I didn't see the negative sign. Okay, thank you. So putting that in the so we have in the sum formula for the tangent of a sum is going to be the sum of the two tangents. So that's going to be the tangent of theta plus the tangent of pi over 2. Uh-oh. No, they're not going to do that because the tangent does not exist here. So we're not going to do that. Because if I get a number that doesn't exist, then I can't use that formula. But I can change it to sine over cosine over sine. No, sine over cosine, which is what they did. Now we can do the sine of the sum of two angles. So my numerator is sine theta cosine pi over 2 plus cosine theta sine pi over 2 being divided by cosine cosine theta cosine pi over 2 minus, since we're adding here in the cosine formula, this is subtraction, and this will be sine theta sine pi over 2. Again, I'm going to look at my unit circle because pi over 2 is one of the quadrantial angles. So the point up here is the x and y for these sines and cosines. Because I can get an exact value for cosine from here, and I can get an exact value for sine from here. So what are the coordinates of this point? 0, 1. So cosine of pi over 2 is what?
0.
So we're multiplying by 0 here. This is 0, and this is 0. So the front half of the fraction disappears. Nice. And what is sine of pi over 2?
1.
Yeah, just 1. So I have cosine theta times 1, which is just cosine theta, and the minus or negative sine theta times 1, which is just the negative cosine theta over sine theta. Well, what's cosine over sine? What's x over y?
Tangent.
Not tangent.
Cotangent.
And since it was negative here, it's going to be negative cotangent, which is what we needed to get. So this is establishing the identity. Okay. And yeah, this where they're going to bring. And then they're going to show that it's sine times 0, cosine times 0, cosine times 1, and sine times 1. Negative sign stays, so it's going to be a negative fraction. It becomes negative cotangent of the thing. Now this one, this gives me an angle. And this gives me an angle. I don't need to know what those angles are. Because, so I'm gonna say cosine of, I'm gonna say cosine inverse of 1/2. I'm gonna call that I call that alpha. And sine of 2/5, I'm gonna call that beta. Because inverse trig functions give you an angle. And what this is saying is that cosine of alpha equals 1/2. And sine of beta equals, what is that, 3/5?
Yes, sir.
And because I'm gonna need to know what sine of alpha is, and I'm gonna need to know what cosine of beta is, I'm gonna create two triangles so I can find the missing side. Okay. So this is the x and this is the radius. And the radius is the hypotenuse. And so the x is 1. And this is 2. So now I need to find out what this side is. So I'm going to square 2 and I'm going to subtract the square of 1 and square root that answer. So 4 minus 1 is 3. So this is going to be square root of 3. And the sine, because we're talking this angle here, the sine is the opposite side over the hypotenuse, because this is the y value and that's the radius. So the sine of alpha is the square root of 3 over 2. I mean, just the square root of, square root of 3 over 2, sorry. Which means this is a 60-degree angle, pi over 3. And with beta, we have the y value is 3 and the r value is 5. So now we need to find the x value down here. So this was alpha and this is beta. Well, that's a 3, 4, 5 right triangle. So this one makes it easy. So cosine is going to be 4 over 5. Now I can use the sine formula, I mean the sine of a sum formula, which gives me sine of alpha times sine of beta, times cosine of beta. Since it's plus here, it's going to be plus here. And then it's going to be the cosine of alpha times the sine of beta. And I just substitute the numbers in appropriately. And I didn't even have to find out what alpha and beta are. So sine of alpha is the square root of 3 over 2. Cosine of beta is 4 over 5, and I'm multiplying those two together. Plus the cosine of alpha is 1/2. And the sine of beta is 3/5. All right, normally I would reduce this fraction here, but since I'm going to be adding two fractions and these both are going to be 10, I'm not going to reduce the fraction. So this becomes 4 square roots of 3 over 10 plus 3 over 10, which is 4 square roots of 3 plus 3 divided by 10.
So it just so happened that they both ended up being 10, so we kind of got lucky. Because we didn't have to like change the number.
Right. Well, if I'd done it the way I wanted to do it, or my initial way of doing it, this would have been 2 square roots of 3 over 5.
Yeah,
But then we'd have to multiply the 2's back in again.
Yeah.
So we get 10 in the denominator. So like if that was 1/3 instead of 1/2. So then it would be the square root of 8, or 2 times the square root of 2. 3 squared minus 1 squared, square root. And so in that case, yeah, we would have gotten 15 in the denominator here. So I would have had to multiply this one by 3 and no, this one by 2 and this one by 3, 2 over 2 and 3 over 3 to get the same denominator. To get 30 in the denominator. I'm going to erase this because they have the same thing. Only they get a little wordy.
a little wordy.
A little wordy. I think they go in directions I don't see as necessary. But we want the sine of the sum of 2 angles. So they're doing the same thing I did, only I didn't state it formally. I just said that I'm going to say this is alpha and this is beta. On an exam, you would need to state that. All right, since cosine is positive, then alpha has to be between 0 and pi. Since sine is positive, that means beta has to do between negative pi over 2 and positive pi over 2. So as long as we have those restrictions in place, then we're good to go. That alpha and beta have to come from those particular domains. All right, so they found them differently using the Pythagorean theorem. I mean the Pythagorean identities. For sine squared equals 1 minus cosine squared, and then you take the square root of both sides. And since sine of alpha is positive, we want the positive square root. And we know cosine of alpha is 1/2. So 1/2 squared is 1/4. And 1 minus 1/4 is the square root of 3/4. And I can take the square root of the denominator and we get the square root of 3 over 2, which is the same thing we got. Only we use the triangles. And they tend to want, since we're doing identities, they tend to use the identities more often. And cosine of beta will work the same way. Since cosine of beta is going to be a positive number, then it's going to be the positive square root of that. And then we know what sine of beta is. It was 3/5, and 3/5 squared is 29/5. I square the 3, I square the 5. And 1 minus that, oh, it's 9 minus, 25 minus, this would be 25 over 25, and 25 minus 9 is 16. So we have 16 over 25, and I can take the square root of both numerator and denominator to 4/5, which is the same number we got.
Sorry, I really like the way you did it.
With the triangles,
Yeah.
it's much easier to understand.
So simple.
The trig identities kind of throw people, and I understand that. Okay. So, yeah, so replacing this with alpha and this with beta, we get this, which is what we had done earlier. And so we would get this sum of these two products. And we know what the sine of alpha and the cosine of alpha and the sine of beta and the cosine of beta are. So we just replace those appropriately, do the multiplies, and add the numerators. And this time they didn't factor 1/10 out of it.
Wow, they left it like that?
Yeah, they left it as a fraction. Which most mathematicians, they would either leave it this way or write it as a sum of two fractions. 2 times the square root of 3 over 5 plus 3 over 10. So now we want to write this as a algebraic expression. That means we just want to use it, write it using U and V. Now here we're going to use the Pythagorean identities simply because it's simpler to do that. So for sine inverse of U, the restriction on U is that it has to be a fraction between -1 and +1, including -1 and +1 because of the equals. And same thing with V. Because sine and cosine only give us numbers that are between -1 and 1. We get other numbers other than that if you're multiplying sine and cosine by something else or adding to the result. So so they're going to say alpha equals this and beta equals that. And so the sine of beta, the sine of alpha equals U, and the cosine of beta equals V. With those restrictions on alpha and beta. All right, sine is between -1 and +1 from -π/2 to π/2. And same thing with cosine. Cosine is -1 to 1 when the angle is between 0 and pi. Well, it's always going to be that, but we're talking about just that restricted domain. Well, it's going to be, yeah. So So we have these two situations again. Where we can write, we can find the sine, the cosine here by doing 1 minus sine squared to give me the cosine. And I can do 1 minus sine squared and square root them to get cosine beta. So that's what they're doing here. All right. So this is just the Pythagorean identity being used to set these up. I know that sine of alpha is u and the sine of beta is v. And so cosine squared is v squared and sine squared is u squared. Okay. And then we just set up the problem. Realizing we know that the sine of alpha is u and the cosine of beta is v. Because that's what was given to us. We understand that. For the sine inverse of u to exist, that means the sine of that angle equals. And so we use the sum, the sine of the sum of two angles. We use that formula. And we know we have an expression for each cosine and sine. Sine alpha is u, cosine beta is v, so this is u times v. Cosine alpha is the square root of 1 minus u squared, and sine of beta is 1 minus v squared, being square rooted. And so you have the product of those two. So it's going to be uv times the product of those two square roots, which is what they have here. They just leave it here. I kind of would too. Or I might put it under one square root symbol. And say it's the square root of the quantity 1 minus u squared times the quantity 1 minus v squared. And then I might even multiply it all out, but that'd be a mess. You get 4 terms. Okay, cosine plus sine plus cosine equals 1. What does that happen? And I will tell you it does happen. It's just you have to find that angle. Well, we need to change the sine and cosine in such a way that we get the sum and difference. So we bring in another angle. All right, option 1 attempts to use available identities do not lead to equations that are easy to solve. So one thing to do is to square both sides of the equation. The right-hand side is easy, you get 1. But the left-hand side, you get sine squared plus 2 cosine theta, 2 sine theta cosine theta plus cosine squared. Now, Do they? I think they do. No, they don't. Sometimes they rewrite it to put the cosine squared and the sine squared next to each other. But sine squared plus cosine squared is 1. So this becomes 2 sine theta cosine theta plus 1. And then they subtracted 1 from both sides. And once you subtract 1 from both sides, you get 1 times the sine theta times the cosine theta equals 0. And what they did here was they divided by 2. So now you have a product that equals 0. You have a product that equals 0. So we're looking at when is sine of theta equal to 0? And when is the cosine of theta equal to 0? Because it doesn't matter which one is 0, it'll make this equal to 0. And when cosine is 0, guess what? Sine will be 1. And when sine is 0, cosine will be 1. Pi over 2? Pi over 2 is one of them. So sine is 0. Well, cosine is 0 at pi over 2 and 0. No, pi over 2 and 3 pi over 2. Sine is 0 at 0 and pi. But we're going to be adding the sine of 0 to the cosine of 0. And we're going to be adding the sine of pi to the cosine of pi. And we're going to be adding the sine of pi over 2 to the cosine of pi over 2. And adding the sine of 3 pi over 2 to the cosine of 3 pi over 2. Which one of these gives us 1? Again, we're dealing with the quadrantial angles, right? And so this is 1, 0, this is 0, 1, and this is -1, 0, and this is 0, -1. Which pairs, because this is x, this is cosine theta, and this is sine theta, which one of these, when you add them together, gives you 1? Do all 4 of them give you 1 when you add them together?
No, only 2.
Only 2 of them. So those are the only 2 angles. Theta equals 0 or theta equals pi over 2. So that's our solution set, 0, pi over 2. Notice they say the apparent solutions are 0, pi, pi over 2, and 3/2 pi. Because then you have to check in the original equation which ones work. Because we squared the original equation, that means it's going to give us more answers than we actually need. These are the solutions. These 4 angles are the solution to sine theta cosine theta. equal to 0. So these four angles are the solution to sine times cosine of those four angles, one at a time. But we weren't multiplying sine and cosine, we were adding sine and cosine to get 1. And so that's where we have to check it. Yeah. And so we do have two extraneous solutions, and that is pi and 3 pi over 2. I have a friend over at San Antonio College that she has her students state the extraneous solutions. So you would state, these are the solutions and these are extraneous solutions. What it means by extraneous solutions is we get those as answers while solving it, but they don't work in the original equation. Because you either squared both sides or you took the square root of both sides, and so you got more answers than what would work in the original equation. And so here they worked them out. And yeah, looking at the quadrant, sometimes going to the unit circle, you can see an obvious answer. It's obvious when I add these two together, I don't get 1. But when I add these two together, I do get 1. So that's why it's 0 and pi over 2. 3/2 pi gave us -1. And pi gave us -1, where 0 and pi over 2 gave us +1, which is what we needed to have happen. And so they wrote it as a solution set, which I suggest you do. And for my friend, this is how she would want your answer read. I just want to know what the solutions are. Now, here's another way. And they're dividing both sides by the square root of 2. So they're giving you options. Now, the left side resembles the formula for the sine of the sum of two angles, one of which is theta and the other is some unknown angle called phi. Yeah, this is a Greek letter phi, P-H-I, I think is what it is. Psi, P-S-I. Looks kind of like a trident where the outside prongs got bent over. But we use this too, but not in this course. I don't remember where we use it. We use Greek letters all the time. In stats, we use sigma, capital sigma, and lowercase sigma. Uppercase sigma denotes a summation, and lowercase sigma denotes standard deviation of the population. And lowercase sigma looks like a circle with a tail. and uppercase sigma, you've seen this. It's like that. With I equals 1 to k, where all these numbers are integer numbers, or zero, usually 0 to k, but and then you have an expression here, and so you do all the numbers from 1 to k in that expression, and you add them all together. That's a series. Series is a sequence that you add up. So 1 through 10, or a classic is 1 through 100. That's a sequence. The integer numbers 1 to 100. If I add them up, that's a series of the integer numbers 1 through 100.
What's the answer, sir?
5050.
Nice.
And there's a formula for that. I used to play a game called, logic game called cross sums. It's like a crossword puzzle, but with numbers. And the numbers would add up to a specific number, and you could only use the digits 1 through 9. And you only use them once.
Yes, I remember you telling us about this. You play with your friends, like send it to each other or something.
No, I just did it. Yeah, I just played it.
Oh, this is just you.
There's free cross sums. The word free, the X, and the word cross, sums.com puts up a daily puzzle that I used to do every day.
Did you get it? Start every day.
And you have to make it up to like to 24 or something like that? You have to make it up to 24?
No, those are magic squares where each row or column adds up.
9, 6, and 7,
Well,
or something like that?
yeah, well, and
9, 8, and 7.
but in magic squares, you have add, multiply, divide, and subtract it. With cross sums, it's just I think Karuku or Kuraku. I can't remember how it's spelled or even
Cockroach?
Kuraku. Sudoku. Well, these are Japanese names to a game, to logic puzzles that have been out there before the Japanese gave them names. There used to be a magazine, I don't know if it's still out there, Dell Games. And they used to have these in it, and they used to have Sudokus in there, but they called them logic puzzles. They didn't call them the Japanese name for them. But anyway, I got off base.
Just a little.
So they're going to say that sine plus phi, and phi equals the square root of phi of. So basically what they're saying is that phi is a 45-degree angle. Right? Because 1 over the square root of 2 is 2 over the square root of 2, and cosine of some angle that equals 2 over the square root of 2 is either pi over 4 or 3 pi over 4. And to get sine of phi to equal the square root of 2 over 2, you're dealing with either pi over 4 or a negative pi over 4. And so the only time those two angles are the same is at pi over 4. So we're just using phi as being a 45-degree angle. So this will be, so that means this is going to be sine plus pi over 4 equals the square root of 2 over 2. Well, that means sine is 0. I mean, the angle is 0. Yeah. That's right. Okay. Okay. So they change it appropriately. So sine has to, so, well, they went the whole circle. And sine is positive in the first and fourth quadrant. And because these are positive, then that kind of restricts what phi can be. Phi is either between, for cosine to be positive, phi has to be between 0 and pi. And for sine to be positive, phi has to be between, well, 3/4 pi, 3/2 pi, and pi, or negative pi over 2 and pi over 2. And yeah, so they didn't go through the explanation like I did of what it is. So the only place that those two domains intersect is in the first quadrant. And so phi has to be in the first quadrant, which is pi over 4. So we have that equation. So we have two angles whose sine is the square root of 2 over 2. So sine is, sine is here and here positive, and cosine is positive here and here. Okay, I had them reversed, but anyway. So we're talking about this angle here, pi over 4, and this angle over here, 3 pi over 4. And phi, since phi is pi over 4, then we need to take pi over 4 away from that, which brings us down to 0 and pi over 2. Because 0 plus pi over 4 needs to equal pi over 4. Beta plus pi over 4 needs to equal pi over 4. And theta plus pi over 4 needs to equal 3 pi over 4. And so in this case, pi is 0. I mean, theta is 0. And in this case, theta is pi over 2, which is the same answers we got previously. Complicated enough for you?
That's a little.
Yeah. All right, so there's our same solution set. They're just getting spooky here now. Dividing both sides by the square root of a squared plus b squared. So now you have this situation. So that's kind of doing the same thing. Kind of, almost, sort of what we did before. Yeah. And so this is would be the sine of phi. And this would be the cosine of phi. Oh, they switched around, that's right. Oh, okay, because they want to do the sine function, right? So they're going to make this the cosine of phi and this the sine of phi. And so we're going to get the sine of the sum of two angles, theta and phi. All right. So from here, we look at what's going to happen. Okay, that if the absolute value of C is larger than so if the numerator is larger than the denominator, then this doesn't work. Because sine gives you a number between -1 and +1. So C has to be smaller. The absolute value of C has to be smaller than this. But C could be positive or negative. Or this down here will be a positive number. So the absolute value of C has to be smaller than the square root of a squared plus b squared. And that's what they're saying. Because if the absolute value of C is greater than greater than that square root, then the sine is going to be either greater than 1 or less than -1, which does not happen with sine. The only way you get a number outside of that range or that domain of -1 to 1, the range, is if you're multiplying by sine by a number, or you're adding something or subtracting something. So sine alpha, theta plus phi is going to equal so they just did the inverse sine on each side. And to get the opposite see if that sign is up here, then the other one is down here. Because this one down here will give us a negative sign, and this one gives us positive sign, and this one down here will give us negative sign, but they're complementary angles. Supplementary. Anyway. So once you determine what phi is, then here we have the solutions to the equation. We don't get any real number answers here because we don't have any real numbers to deal with. All we have is alpha, A, B, and C, and some angle phi that we can throw in for the measure. So once we're given an equation where we know what A, B, and C are, then we can take the inverse sine of this and we can subtract that angle from pi to get the negative, and there'll be and then we can subtract phi from this to get the positive. So this part here, these two parts here are the same number here and here. It's just one of them puts us in the first quadrant, the other one puts us in the third quadrant, and one of them puts us in the second quadrant, the other one puts us in the fourth quadrant. So we could have up to 8 solutions here. Like that. Okay. Double angle and half angle formulas. Double angle formulas, we're going to find out what they are and use them. We're going to use and find out, find exact and use them to find exact values and to establish identities. And then use half angle formulas to find exact values. Which means by using exact values, you leave the square root symbols. You don't type it into the calculator. Okay. Here are 4 double angle theorems. And something that should be quite obvious is that cosine of 2 theta has 3 different formulas. Three different formulas. This one, I can rewrite cosine as 1 minus sine squared theta minus sine theta.
Camera's off.
That's exactly.
Oh man. My you know, the window, the taskbar on the bottom of the Zoom window, it's not there. Jesus. Uh-oh. Ah. That wasn't supposed to happen. Zoom just disappeared. Oh, it's still there. Only it's not pulling up. Uh-oh. Okay, the closed caption is still active and I can still see it here. Closed caption, not closed caption. Yeah. Anyway, But nothing else is moving, nothing, my mouse is moving around. But I click on anything and nothing happens. Don't you just love Zoom?
So we still can't see nothing.
Yeah, I know. And my screen is frozen. I mean, I can move my mouse around and I can see the closed caption across the bottom, but I can't do anything. So what's gonna happen is let me see. Hopefully this will just close down things, not restart things. Nope. Still not doing what it's supposed to do. So what I'm may end up having to do here, and it'll take me about anywhere from 5 to 10 minutes to get back in. Oh wow, wait a second. I thought about trying that. Taskbar. Nope, I want settings. I want task manager. And it won't let me do that either. I'm not an administrator on this machine, so I can't do that. I'm just gonna have to restart the machine. And hopefully Zoom stays open and it assigns someone as the host of the room. And I'll come back in as soon as I can.
Okay.
This is pissing me off. Well, I can pull it back now. That pulls up. That comes up. And that came up. Oh. The Zoom isn't coming up. So let me see if it'll let me. Close out the Zoom. Not have to restart the machine. Restart the machine. Oh, I hate this. Now what I can say. Okay, I'm gonna have to restart my machine. Let me try this.
Yeah, so what's going on here?
Okay, can y'all hear me?
Yes, sir.
Okay. Unfortunately, you can't see me, can you?
Nope.
No, we still can't see you.
And maybe that will sign note. You're supposed to, oh, is it, what screen is it sharing? What is showing on y'all's screen in there?
Double
It
angle
says double
formulas.
angle formulas.
So you see the double angle theorems in the shared screen?
Yes.
Okay, cool. So that's what we're gonna have to work with. Because it's not reading the camera. Probably should have spent the time to set up the camera I brought. Anyway. let's set it up time. Okay. So with equation 2 of the double angle theorems, if you replace cosine theta with 1 minus sine theta, you'll get the equation 3. And also in equation 2, if you replace sine squared theta with 1 minus cosine theta, you wind up with equation 4. Yeah, y'all can't see me pointing at the board, but that's what I do. We got people leaving. So you got the shared screen and you can see me here, right?
Oh yeah, I can see you in the tiny screen, top right.
And you can see the
Yes, I can see the double angle theorem or theorem of double angle formulas.
so all right. So if I put 1 minus sine squared in here, I get this because I have 1 minus sine squared, which is 1 minus 2 sine squared. And if I put 1 minus cosine squared in place of sine here, then I have the minus 1 minus the cosine squared. So minus 1 becomes minus the 1 becomes minus 1. And minus the minus cosine becomes plus the cosine. So we have 2 cosine squared theta minus 1. So these two formulas here are derived from this formula up here. Okay.
Transcription closed, captioning is there.
It's not doing what I want. Okay. So now we have sine of theta equals 5/6. Find the exact value of 2 sine theta and 2 cosine theta. Well, all right, so we're talking about being from pi, theta being from pi over 2 to pi. So we're talking about this quadrant. where the cosine is negative and the sine is positive. Okay, so rewriting this using the double angle theorem for sine, which is 2 times sine theta cosine theta. So this, and I know that sine of theta is 5/6. So cosine theta, well, I square 6 and I square 5 and I do 36 minus 25. So I find this number down here, which is going to be the square root of 11. And so that's what we have down here. But it's going to be negative because we're in this quadrant, so x is going to be negative. So that means the cosine of the same angle is going to be the negative of the negative square root of 11 divided by 5. And yeah. And so they found the square root of 11 the same way I did, the negative square root of 11. And it's going to be negative because a in this case has to be a negative number. And then they pulled the negative sign out front, which is something I always do as well. So now I can replace cosine theta with the negative square root of 11/6 and replace the sine of theta with 5/6. And so the sine of 2 theta is going to be the sine of the theta times cosine of the theta. Right? 2 times that. So 2 times sine theta cosine theta. Sine theta equals 5/6. Cosine theta equals a negative 11 square root of 11/6. And so we multiply those together and then multiply by 2. Okay, I can reduce here first. And so this will be the negative 5 square roots of 11/18. Right? Because the 2 and the 6 reduce to 1/3. So that's a 3, and 3 times 6 is 18. And then we just multiply the numerator. And it stays a negative fraction because we're only multiplying by one thing. And cosine 2 theta. So backing up to that formula, sorry about this. We know sine of theta, we know cosine of theta. So I can use this to find the cosine of 2 theta. Oh, no, they're using a different one. They're going to use cosine of 2 theta equals 1 minus sine squared. Because we know what sine is. Sine is 5/6. So 5/6 squared is 25/36. And 5/36 times 2 is, 25/36. becomes 25/18. And 1 minus 25/18 is a negative number. -7/18. Because we want to turn 1 into a fraction of 18/18. And so once the denominators are the same, the action happens in the numerator. So 18 minus 25 is a -7. So there we have it. All these formulas, all these trig identities and formulas, you will have a worksheet that will have them all on there. I'm going to put that in the files, so you don't have to memorize all these formulas. I know that was a concern.
Thank you, sir.
Well, I never had to memorize them either. The only reason some of them sit in my head is because I teach it all the time. The more you use it, the more it resides there. Unless like you're like me, you start forgetting a lot of shit. CRS is a real disease. Okay. CRS.
What's that, sir? Come on.
You know what CRS is? Can't remember shit.
Oh.
All right. So
I get a severe case when I'm doing tests.
what?
I said I get a severe case of CRS when I'm doing tests.
Yeah, a lot of us do. That's also a case of brain freeze. Or you walk into the testing area and you have a brain dump. Craps out on you. Develop a formula for tangent of 2 theta in terms of tangent. Develop a formula for, okay. Well, the only one we really need is A. If we have time, I'll do letter B. But tangent, right? Tangent of 2 theta is the same as the tangent of theta plus theta. So now I can do the tangent formula of the tangent of the sum of 2 angles, which will be tangent theta plus tangent theta divided by 1 minus tangent theta times tangent theta. Right, so we have this, but alpha and beta are theta because they're the same angle, because theta plus theta is 2 theta. And that's the next step. And so simplifying my expressions in the numerator and denominator, you have 2 tangent theta divided by 1 minus tangent squared theta. So this is the sum, this is the double angle formula for tangent. So we have a double angle formula for sine, and we have 3 double angle formulas for cosine. And here's a double angle one. Let me just get the whole picture. Higher than humidity. Okay. Yeah, okay, we still got time. Now, to convert this, instead of using 3 theta, we can use 2 theta plus 1 theta. So 2 theta plus 1 is the same as 3 theta. So now I can use the sum property, the theta, sine of the sum, which gives us sine, cosine, cosine, sine of 2 theta and cosine. And now we can use the double angle theorem formula for sine of 2 theta and for the cosine of 2 theta. So it just all depends upon which one they chose to use. Oh, and they used cosine squared minus sine squared for the cosine of 2 theta. And the sine of 2 theta is 2 times sine cosine. And then you do the distributive property, or do they do it? Yeah, they did. This is just going to be, we're just multiplying cosine times cosine to give the 2 cosine and to get the cosine squared. And then multiplying in by sine, we have sine times cosine squared minus sine to the 3rd power, because sine theta times sine squared is sine to the 3rd. And there we be done with that. Now, this isn't exactly a formula. Well, it is, but it's not something we really worry about. They simplified it. How do they simplify it? What happened here? Oh, because this is sine cosine squared. This is sine cosine squared. So I'm adding one of them to 2 of them, which gives us 3 of them. I didn't even notice that. Go home. There. In about 3 minutes, I can do that. And here are more formulas. Sine squared is 1 minus cosine 2 theta over 2. Cosine squared is 1 plus cosine of 2 theta over 2. And then tangent squared is 1 minus cosine over 1 minus cosine 2 theta over 1 plus cosine. All right. Tangent is sine over cosine. So tangent squared is sine squared over cosine squared, and that's all they did. And simplify the fraction. Multiply numerator and denominator by 2 to get rid of the denominators. And so we just have the tops of those 2 fractions in these 2, where 1 minus is in the numerator and 1 plus is in the denominator, because that's where the sine and cosine is. Yeah, these can be fun. Oh, I had to memorize those. That was ugly. Couldn't do it.
Oh, so you wrote on your hand.
No. What is that? Cosine inverse or? Yeah, I know. Maybe it is a 4. It is a 4. So what that is cosine squared times cosine squared. To use not formula 7 twice. Cosine squared squared, right? X squared is x to the 4th, and that's what they're using here. So we're squaring this. So 1 plus cosine 2 theta divided by 2 we're gonna square that, so my denominator becomes 4, my numerator becomes 1 plus 2 times cosine 2 theta plus cosine squared 2 theta. Right? Only they brought the 1/4 out, and I would have left it in, I don't know. why. So cosine 2 theta, we have two options here, but we want to have just sine or cosine. And okay, so yeah, so they're done with this part because we just want cosine and sine to be in a single power. I just would have had the whole thing over 4. All right, we'll start with this slide next time. And I'm gonna bring my camera again next time and set it up just in case.
All right, sir. I guess this is a goodbye until next week. Now, this time I'm correct. Last Tuesday, I thought that Tuesday was Thursday. This time it's actually Thursday.
All right, we'll see you on Tuesday. Enjoy your weekend.
Bye, everyone.
Yesterday I had a class where nobody showed up.
Class where no one showed up?
Yeah, my largest class too. Well, they're high school students and they were doing PSAT and SAT testing this week. And so they were excused from class.
I don't know, that's cool. I'm happy for them that they are in high school and doing college, but in my bio class, I have to do a group project. And it's 4 of us and 3 of them are high school students. So I'm here on campus, normally around like 9 a.m.
Uh-huh.
And they can't come to campus because they're in high school. So it's like difficult trying to meet up. And it even sounds weird now that it's coming out of my mouth. It's weird trying to meet up with high school kids. But we need to work on a project, so it's just strange. They're all, we have homecoming, we have this, we have that, the little high school things. You have a good evening, sir.
You too. I'm having troubles getting rid of this Zoom. Well, there it is. Okay.